Bismillahirrahmanirrahim. Assalamu alaikum wa rahmatullahi wa barakatuhu. Welcome back, dear students. As you know that in the last couple of lectures, I discussed the analysis of faults. We in the beginning covered faults in general, what is basically a fault in a power system. And then we discussed the classification of faults, and majorly we discussed that there are two types of faults. One are balanced faults and the other types are unbalanced faults. And then we discussed the balanced faults theoretically, and we also discussed the method to analyze the balanced types of faults. And afterwards then I solved a problem to get more clear understanding of the theoretical concepts. After covering the balanced faults and their analysis, then we start the unbalanced fault analysis, and I talked about the symmetrical components. So we discussed that unbalanced faults could be of different types. For instance, single line to ground fault or line to line, or other types could be, let's say, an open conductor. So these are all different types of unbalanced faults. And then we mentioned that the easiest method to analyze unbalanced systems where unbalanced fault appear. So the easiest way is to analyze the unbalanced system is through the use of symmetrical components. And then we discuss the symmetrical components that, for instance, is, let's say, a two-bus system where an unbalanced fault, let's say, appears, and then the three-phase quantities will no more be balanced, meaning to say that their magnitudes will be different. So it is illustrated here. One can see that, and even we discussed this before, but I am revising the previous contents. So one can see that the magnitude of the three-phase currents are different, and this unbalanced system, through transformation matrix, we convert the unbalanced quantities into three set of balanced quantities, which are known as zero sequence components, positive sequence components, and negative sequence components. Each of these three are balanced in the sense that here the quantities or the components have equal magnitude and they are in phase. Here they have equal magnitude and phase shifted by 120 degree, and also here this is the same case. The magnitudes are equal and they are phase shifted by 120 degree. So this is we have discussed before. And then after discussing the theory, I even solved two problems to make the theoretical understanding more clear. So we solved two problems. We took the case of a balanced system with ABC sequence, which in other words mean the positive sequence. So we determined the sequence components of the phase voltages, and for that I have discussed that for converting the phase quantities into the sequence quantities, we need the transformation matrix. We have discussed this before, but I am just revising the previous contents. And for converting phase quantities into sequence components, one can first determine the inverse of the transformation matrix. Multiplying it with the phase quantities, one get the sequence components, and these are zero, positive, and negative sequence components. And after solving this problem, we found that since the system is balanced, as one can see, the magnitudes are equal, phase shifted by 120 degree. So we found that this system, as it is the positive sequence, so only V1 exists, only the positive sequence exists. The values of the other two sequence components, zero sequence and positive and negative, they were found to be zero. We have already solved this problem. So with the ABC sequence, we found that if we even convert the phase quantities into sequence components, we found that only the positive sequence exists and the other two sequences have 0 values. And then we took an example of a unbalanced fault where we considered, let's say, that one of the phase is open, which is basically one of the type of unbalanced fault, as it is shown here that the value of the current in phase B is 0. So this is basically an unbalanced fault. And then we found that by decomposing the phase components of the current into the sequence component, we found that all the three sequence components have certain values. So in an unbalanced system, all the three sequence components, zero sequence, positive sequence, and negative sequence currents, we found that they have certain values. So for a balanced system, if it is, let's say, the positive sequence, ABC sequence, then we found that only positive sequence exists and the other two sequence components are 0. But if it, let's say, we take the example of an unbalanced system, then all the three sequence components have certain values. So we discuss these two problems and we get a more clear understanding of the theoretical concepts. Today I will continue with the unbalanced faults, and we will talk about the sequence networks. So we are still talking about the unbalanced fault analysis, and today I will talk about the sequence networks. So we discussed the sequence components in the last two lectures, and as I mentioned, we even solved problems to get a bit clear understanding of the theoretical concepts, or how to apply the transformation matrix to convert, let's say, the phase quantities into sequence components, or if, let's say, the sequence components are given, to convert it into the phase components. So we use the transformation matrix, and we have already discussed this quite in detail. So today I will talk about the sequence networks, and we once again are discussing unbalanced faults. So let's start with the today's lecture. So we will discuss in today's lecture about the sequence networks. What are sequence networks? Sequence networks are basically sequence impedances. These are the impedances or the impedance of a equipment or a component offered to the current of different sequences. So it is, the definition is quite simple. The impedance offered to the sequence currents are known as sequence impedances. And obviously, if they are, let's say, are supposed to be currents and impedances, we will have the sequence networks where we have impedances also currents. And we also mentioned that we have sequence voltages. So voltages, sequence voltages, sequence currents, and sequence impedances together, it will constitute what we call a network. So the impedance offered to the sequence currents are known as sequence impedances. And as we have discussed that there are three sequence currents, positive, negative, and zero sequence currents. So correspondingly, we have a positive sequence impedance, what we represent with Z1. If you remember, we represented the current I1, what we call basically the positive sequence current. So correspondingly, we represent Z1 as the positive sequence impedance. Similarly, we have Z2 and Z0. So these are the negative and zero sequence impedances offered to the negative sequence current and the zero sequence current respectively. So once again, sequence impedances are impedances offered to the sequence currents. And now it will take me a couple of lectures to talk about the sequence impedances of power system components. And you know that power system components, like for instance transmission lines, loads, rotating machines, transformers. So these are all different components of the power, of the power system. So we will discuss each of these components one by one, and we will discuss how to determine the sequence impedances of all these components of power system. So I will try to cover in this lecture the sequence impedances of the Y connected loads, and it will take me a few more lectures to cover the rest of these components. So let's talk today about in this lecture about the sequence impedances of Y connected loads. So this is the situation here. Or we are considering, as I mentioned, we are considering Y connected loads. So this is basically a Y connected load where the neutral, as one can clearly see, the neutral of the load is grounded through the impedance Zn. So each phase impedance is considered as Zy because we are talking about the uh, balanced loads, let's say, where the magnitude of the impedance in each phase is the same, and the neutral is connected to the ground through the impedance Zn, and that is the current In which is flowing through the neutral impedance. And similarly, we have phase A current, phase B current, and phase C current, and each phase impedance of the load is represented as Zy. So now by applying, let's say, the what we call the Kirchhoff voltage law, so you are familiar with the voltage, the different rules. So now as one can see that the voltage from, let's say, point A to the ground, which is we represent with VAG, as the subscript clearly indicate that G is the reference point, A is the phase A, and V is the voltage. So this is basically the voltage from phase A to the ground. It can be written as a product, a sum of the voltage drop across the impedance Zy plus the drop across the neutral impedance. So that will be equal to ZYIA plus IN and ZN. So it is even it is mentioned here. So the voltage drop from point A to the ground will be sum of the voltage drop across the let's say the ZY, which is the load in the phase A, plus the voltage drop across the neutral, through the impedance Zn. So now as we also know that the neutral current, it is the sum of the three phase currents IA plus IB plus IC. So these are the three phase currents, and now putting Zn as a sum of these three currents, we will get this particular situation. It is quite clearly mentioned here. So this is now the case where the neutral current is replaced with the three phase, the sum of the three phase currents, and we know that from the discussion we have made earlier. So now as one can see that the current IA is flowing through the impedance ZY, also it is flowing through the impedance Zn. So we can take the phase A current common, and now this is basically the impedance, which is a sum of the ZY, which is the load impedance in the phase, plus Zn. And similarly we have another term which is the product of the Zn and the phase current IB, and we have the other component what is equal to the phase C current plus the Zn. So now we will get these terms. Similarly, now by analogy one can write for the other two voltages. The voltage VG will be equal to, as the current in the phase B will flow through the impedance ZY, also because neutral current have the phase current, so this will also flow through the Zn impedance. So by analogy what we have discussed here, we can also now put the the voltage from point A to G, which is the ground, equal to Zn IA plus, as I mentioned, the phase B current will flow through the impedance ZY plus Zn plus the Zn IC. So now this is the case. So and similarly the expression for the other phase voltage from point C uh, point C to the ground is also written here, which is sum of these three terms. So now all these three terms we can write in the matrix form, because we have some terms that are common. So now let's writing these three phase voltages in the matrix form. So as one can see, that the term let me write. So let me write all these three voltages in the matrix form. So the matrix form will look like that. So this is the matrix form, where these are the phase voltages, and on the right side we have the impedances and the phase currents. So the expression we have discussed just before, now we are writing these expressions in the matrix form. So now this is basically the matrix form, where these are the phase voltages, these are the phase currents, and this is the phase impedance matrix. So this matrix represents the phase impedance matrix, and this is the this vector, this matrix is the represent the phase currents, and these are the phase voltages. So now if you remember, we discussed even in the in the beginning of this lecture, where I revised the previous contents, we discussed that the phase voltages can be written as a product of the transformation matrix A and sequence voltages. And similarly, these currents can also be written, where the phase currents are equal to the transformation matrix A and the sequence current. So now let's using that information, so we can write that the phase voltage will be equal to transformation matrix A into the sequence voltage, and similarly the phase current will be equal to the transformation matrix A into the sequence currents. So we are using now this information, and now we can write the let's say this phase voltage is a product of the transformation matrix and sequence voltage, which is written here, and the phase impedance matrix, this is the phase impedance matrix which appear as it is, and the phase current, this phase current is written as a product of transformation matrix A and the sequence current, which is put here. So this is the phase impedance matrix. This is basically the phase voltage, which is written as a product of the transformation matrix and the sequence voltage, and this is the phase current. So now if let's say we take we multiply both sides with the inverse of the matrix, so we will get from this particular expression, where it is written as let me even put it here. So now using these relations, we can write the phase voltage as A Vs, which is equal to the Zp, which is the impedance matrix, into the phase current, which can be written as a product of transformation matrix A and the sequence current. So if we now multiply both the side with the inverse of the matrix, we will get here Vs equals to A inverse, the inverse of the matrix, into the phase impedance matrix into transformation matrix A into the sequence current. So now we call basically the product of these three matrices as sequence impedance, because now on this side we have sequence voltage and here we have the sequence current. So now this will be the sequence matrix of the sequence impedance, and so now we call these three terms, and the product of these three terms, as sequence impedance. And for that we need to take the inverse of transformation matrix A, also the transformation matrix, and the impedance matrix, which is shown here. So now let's find the sequence impedance matrix, and it is, I believe it is clearly visible here, that now this is, we need to know the inverse of transformation matrix A, which is this is we know from the previous discussion, this is the same matrix which is the phase impedance matrix, and this is the transformation matrix A. So this is the transformation matrix A, this is the phase impedance matrix, and this is the inverse of the transformation matrix A. So taking now the product of these three matrices, we get, because you are familiar with the multiplication of the matrices, so I will not go step by step into those discussion. You are familiar with that. I will directly write the answer. So now by taking the product of these three matrices, we get the sequence impedance. As I mentioned, this is basically the sequence impedance. So now after taking the multiplication of the three matrices, we reduce to this matrix. So now the sequence impedance matrix is equal to this matrix. And once again, after knowing the sequence impedance, as I mentioned before, that now we can write the sequence voltage as a product of the sequence impedance and the sequence current. So once again, the sequence voltage matrix can be written as the sequence impedance into the sequence current, and we have found the sequence impedance matrix here. So now I can write this matrix as a matrix having three components. This is this matrix having three components. This is basically the Vs matrix, the sequence components of the voltage. This matrix represent the sequence components of the current, and this is the sequence impedance matrix. So now we have found that this is the sequence impedance matrix. So from this particular matrix, which is the diagonal matrix, because the off diagonal terms are zero, only we have diagonal terms, and we know that this is the zero sequence voltage, this is the positive sequence voltage, and that is the negative sequence voltage, and correspondingly the currents are written: zero sequence current, positive sequence current, and negative sequence current. So now as one can clearly see that these three networks, or we can write that V naught, which is the zero sequence voltage, it is equal to the product of this term into the I naught, because the other terms are zero. So we have written it like that. So now the zero sequence voltage is equal to the product of the zero sequence current into the Zy plus 3Zn, which can also be written like that. So this is now Z naught is the zero sequence impedance, which is best here. And Also V1, which is the positive sequence voltage, can be put as product of the ZY into the positive sequence current, and similarly for the negative sequence voltage, negative sequence voltage. So Z0, Z1 and Z2 are 0, positive and negative sequence impedances. So now these are basically, and one can, I mean, clearly, as I mentioned in the beginning of this lecture, that in this particular lecture we are talking about the sequence networks. So now, after carrying I mean this discussion, now we can draw three sequence networks based on the these expressions, where the quantities are basically not coupled. We can independently draw three different circuits, what we call the three different networks. So based on these expression, now we can draw three networks, and let me show you those networks. So these three networks are uncoupled, I mean they are independent. Neither of the current is flowing in the in the impedance which is, let's say, common. I mean there are no common terms, in simple words. So each sequence voltage have different terms. So based on these expression, we will now draw three different circuits which are not coupled, which are uncoupled networks. So now based on these three expressions, let me draw three networks, or let me show you the three networks. So this is now V0, which is equal to the product of the sequence current I0 and the sum of the phase impedance plus 3Zn. So that is shown here equivalently like that. This is V0. V0 is the zero sequence voltage, which is represented or shown here as a network having two impedances. One is the phase impedance, one is the neutral impedance, and that is the current I0 flowing because of this zero sequence voltage. So now I have shown the zero sequence voltage as a network where the current I0 is flowing through the two impedances. One is the phase impedance and one is the neutral impedance. So the other two networks can also be drawn based on the these expression, where V1 positive and negative sequence voltages. Now the networks are also drawn here. So this is the positive sequence network, this is the negative sequence network, and that is the zero sequence network. Now, as one can clearly see here, I mean, we need to now derive some important points, that Z0, as one can clearly see, Zn, which is the impedance to the ground, basically. Zn, which is the impedance to the ground, is only appearing in the zero sequence network. It is not appearing in the positive and negative sequence network. Also, the currents I1 and I2, which are the positive and negative sequence currents, they are flowing only through the phase impedance, but not through the Zn, which is the impedance to the ground. So let me find this circuit. So the positive and negative sequence currents, they are only flowing through their respective phase impedances, but not through the impedance which connect the neutral point to the ground. Through this particular impedance, only the zero sequence current is flowing. So Zn, which is the impedance to the ground, it is not appearing either in the positive sequence network or in the negative sequence network. It is only appearing in the zero sequence network. And these two sequence currents, positive and negative, it is only flowing in their respective networks, but not in the through the impedance to the ground, which is Zn. And another important point is that, as we have found that this expression, which is basically if one look here, we can also put it like that the voltage drop, because we have the current, in the zero sequence network, the current I naught will make a voltage drop across Zy, but also across the Zn, but here we have a term 3. So the voltage across the impedance to the ground, from the neutral point to the ground, which is this one, through this impedance the current I naught is flowing. So the voltage drop will be equal to the product of I naught and 3Zn, which can also be written like 3 I naught Zn. And if you remember, we make this discussion even before, that 3 I naught is basically equal to we made this discussion before, this is equal to the neutral current. So it is actually a product of the current flowing through the neutral into the Zn, because 3 I naught is equal to the current flowing in the neutral line. So actually it is a product of the In and Zn. So this is basically another important observation. And now important point is to mention here that, because if you remember, we discussed that in the balanced networks, like we took the case of the voltages. If you remember, we discussed that in the case of the balanced system, let's say ABC sequence, we found that there is no zero sequence impedance or zero sequence voltage. The value we found was found to be 0. And we found that in this particular case only the positive sequence exists. Similarly will be the case of the current. If we have balanced system where balanced currents are flowing, we will have now zero sequence current. And we found that when we took the case of the unbalanced situation, we found that in this particular case, when we solved this exercise, you remember that we found that all the three sequence current have certain values. But let's say if we take the case of the balanced system, then we will have only let's say if it is ABC sequence, we will have only positive sequence current. The other two sequence component of the current will be 0. So if we let's say take now the example of the unbalanced case, then obviously there will be a flow of current through the impedance Zn, which is the impedance connecting the neutral point to the ground. So if let's say that current, then if the neutral current is flowing, because the neutral current in the balanced system is 0, meaning to say that we discussed that even yesterday, that in a balanced system neutral current will be 0, which means I naught is 0, because it is a product of 3 into I naught. So if in a balanced system neutral current is 0, it means I naught is 0. So in that case, if let's say I naught is 0, it means that there will be no current flowing to the neutral, through the Zn. So if there is no current flowing, it means the voltage drop will be 0, and then this point and this point will be the same, because there will be no voltage drop across the Zn. But if we take the example of the unbalanced situation, where the current I naught is no more 0, we have already talked about it. So then it means that in that case, the voltage drop, let's say if we let's say take the, once again, if we take the balanced case, then for the balanced situation case, because the current flowing through the neutral impedance will be 0, so it means that as this is the neutral point, so as there is the neutral current is 0, so this point and this is exactly the same, so which means that VAN will be equal to VAG, as the current through the Zn is 0. So this point is the same, so VAN will be equal to also VAG. But if we take the unbalanced situation, if we take the case of the unbalanced, if we let's say have unbalanced case where an unbalanced fault appear, and then we have also unbalanced case, so I node is no more 0. I node is not 0 anymore. And if it is not 0, it means that some current will flow through the impedance Zn. And in that case, then neutral point and the ground point is no more the same. So in that situation, VAN will not be equal to VAJ. But in the balance case, yes, because then the current through the impedance Zn is 0. So now we have talked about the sequence impedance of Y connected loads, and we made some important observation. The observation we made are that we get three networks that are uncoupled, and we found that in the zero sequence network the current I node is flowing. It is not flowing in the in the other two networks, and the other two networks, the other two sequence currents are not flowing through the impedance to the ground. It is the only, the current which is flowing through this Zn is I node, or rather 3 I node. So, but because 3 I node is equal to the neutral current, so we found that through the impedance to the ground only the current I node is flowing. And then we also made some other discussion. So now, as we have found from here that, let's say, if the neutral is connected to the ground and we have an unbalanced situation, then the neutral current have a certain value that is equal to 3 I node, and that will flow through the impedance to the ground. But let's say if we have the case where the Y connected loads have the neutral not connected to the ground, then this will be an open path. So let's take now that case where the Y connected loads have neutral point not connected to the ground. So this situation is shown here, where it is shown as an open circuit. So if the Y connected load have an ungrounded neutral, then it means that the current I node which is flowing in the zero sequence network will be 0, because we have infinite resistance which is shown here. The neutral point is no more connected to the ground. So the situation will be like that. So this particular case for a Y connected load when the neutral is not grounded is shown like that. So it is an open circuit, and the current flowing obviously will be 0. So for a Y connected load, when the neutral is connected to the ground point, the current, we will have a zero sequence network where the current I node will flow through the impedance to the ground, and that will be 3 I node. In other words, that is the neutral current, and we made those observations. So, but if let's say we take the case of the Y connected load where the neutral is not grounded, so then the sequence network will look like that. The other two sequences will be the same, because we found that the current I node is only flowing in the zero sequence network, and the other two sequences will be the same, but the zero sequence network will look like that, where it will be an open circuit. So that is the case where the I node will be 0. So now we have discussed about we have discussed about the Y connected loads, and let me now further add to this point that, let's say, if we take the case of the balanced delta connected load. If we have a delta connected load, then the situation is shown here. And if you remember, we even discussed that if we have a balanced situation, then it can be equivalently shown as a Y connected load, where the impedance in the each phase of the Y connected load will be equal to, so Zy will be equal to Z delta divided by 3, and that is shown here. So this is the equivalent representation. Now, as we know that in a delta there is no neutral, so it is the same case where the neutral is not grounded, meaning to say that once again the zero sequence network will be an open circuit for this situation. I mean, we just have discussed that if, let's say, the neutral is not grounded, if the neutral is, let's say, not grounded, so then we will have an open zero sequence network. So if, let's say, we connect, I mean, if we transform the delta connected load, a balanced delta connected load, if we, let's say, equivalently showing it by a Y connected load where the each phase load is equal to the Z delta, the each phase load divided by the 3 of the delta connection. So we know that from the previous discussion. So now for this case where the neutral is no more grounded, the zero sequence network will be open and the other two sequence network will appear the same, where Zy obviously will be equal to Z delta divided by 3. So that is equal to the positive sequence impedance and this is the negative sequence impedance. So I mean, only when the neutral is not grounded, then the zero sequence network will be open and obviously the current I naught, which is the current, once again important is that I naught only flow through the impedance to the ground, and since the neutral is not grounded, I naught will be 0. Other words, the circuit is open. Also important to mention here is that these currents now flowing I mean in the Y connected load, of course we have converted the delta connected load into the Y connected load, and I mean we have discussed that Zy now in this case will be equal to Z delta divided by 3. So these current which is now flowing through the each phase load, let's say, and we found also the, I mean we discussed the sequence network. So I naught, I1, I2, which are the sequence current, these are the sequence component of the line currents feeding the delta load, because the original circuit was the delta connected load. So now the sequence currents are those currents which feed the delta connected load. It is not basically the current flowing inside the delta connected load. This is important to know that the sequence currents, because we have now found for the Y connected load these three sequence networks. So correspondingly these three sequence currents, these are the currents which feed the delta connected load. These are not the currents which is flowing inside the delta connected load. This is an important point. So these are, I mean these three sequence currents are the currents which feed the delta connected load, but not the current flowing inside the delta connected load. So this is important. Now let me solve a simple example where it is shown that a balanced Y connected load is connected in parallel with a balanced delta connected capacitor bank. The Y connected load has a impedance 3 plus J4 per phase, and its neutral is grounded through an inductive reactance equal to 2 ohm. Capacitor banks have a reactance 30 ohm per phase. So draw the sequence networks and calculate the load sequence impedances. So for this particular situation where a Y connected load is connected, I mean it is in parallel with a delta connected capacitor bank, and the impedance of the each phase of the Y connected load is given. Also the impedance to the ground is also given, where the Y connection, I mean the Y connected load have a neutral which is connected to the ground, and the reactive inductance is 2 ohm, and also the each phase capacitance, capacitive reactance is 30 ohm. So we are supposed to draw the sequence networks for this particular situation, and also we are supposed to calculate the load sequence impedances. So as I mean the Y connected load is in parallel with the delta connected capacitor. So this situation is shown here, where the Y connected load having the neutral point connected to the ground through the Zn, and Zn in this case is given as 2 ohm, only inductive reactance. So this is the Y connected load, the neutral is connected to the ground through Zn, and this is the capacitor bank which is in parallel with the Y connected load. So I mean this is now the illustration of the case where the Y connected load is shown in parallel with the delta connected capacitor bank. So this is illustrated here, and now the task is to find the sequence networks and also to calculate the load sequence impedances. So as I mentioned that because the two let's say Y connected load and the capacitor bank, they are in parallel. So now the sequence networks, for the zero sequence network, where the phase impedance, also the 3Zn is shown, and it is in parallel with the capacitor bank. So as I have discussed that we can equivalently shown the delta connected load as a Y connected load, where the each phase impedance will be equal to the Z delta divided by the 3. So now as delta connection have now neutral point, or there is no neutral, so that's why this is shown as open, and this is Z delta divided by 3. So now this is the that of the case of the load, Y connected load, where the neutral is grounded through Zn, but we have found, in the previous case where we found the sequence sequence networks of the Y connected load, we found that the zero sequence network have a currents that is I naught, which is the zero sequence current, and flows through the Zy and 3Zn. So that we discussed before. So now we just take the case where another delta connected capacitor is in parallel with the Y connected load, so, and we can equivalently show it as a Y connected case. So that is basically the case where for the zero sequence network it is shown as open, because in delta there is no neutral point. So now it is shown as open, but the other two networks have a complete circuits where we have the Zy and also the Z delta divided by 3, which is the equivalent impedance of the Y connection when we transform the delta connection into the Y connection equivalently. So that is basically the other two networks, positive and negative. So this is positive, I think I shouldn't have drawn it. So this is now the positive network and this is the negative sequence network. So we are supposed also, we were tasked to find the sequence networks of this particular case where a Y connected load is in parallel with the delta connected capacitor bank, and we are also supposed to find the load sequence impedances. So now the zero sequence impedance will be equal to, as it is clear, the other side is open, so that will be equal to Zy plus 3Zn. We made this discussion even in the beginning of this lecture. So as Zy is given as 3 plus J4, and Zn, which is only the inductive reactance, that is 2. So because the 3 term, the factor 3 is also appear in the zero sequence network, so we multiply 3 with the inductive reactance to get the total zero sequence impedance, and that is equal to 3 plus J10. So that is the zero sequence impedance, which is equal to Z0. And also because these two are in parallel, so one can further carry this these steps to find the positive sequence impedance and also the negative sequence impedance, because the two are in parallel. And it was mentioned that the per phase capacitive reactance is equal to 30 ohm. So we first have to divide it by 3, because we are equivalently converting the delta into the Y connected case. So we divide first the Z delta by 3, and it is equal to J30. So and this is capacitive reactance, so we put also a negative sign, so it's minus J30 divided by 3, so it will become minus J10. And we take now this, because it is in parallel with the Zy, so we take Zy in parallel with the this value, so we get the positive sequence impedance is equal to 7.45 with an angle of 26.5 degree, and similarly Z2 is the same, because situation, this is the two circuits represent, let's say, more or less the same terms, so this will be the same what we have found before. So now with this discussion I end this lecture. And let me quickly revise the or summarize the contents. We discussed we started this lecture with the revision of the previous lecture, and then I talked about the sequence network. As I mentioned, that we are talking about the analysis of the unbalanced faults. And for the unbalanced fault, the easiest way to to analyze the unbalanced faults through the use of symmetrical components. So we have already discussed the symmetrical components and sequence components, and in this lecture I talked about the sequence networks, and I mentioned that networks are networks where we have sequence impedances, also sequence currents and sequence voltages. So sequence impedances are basically the impedances offered to the sequence currents, and I discussed that we will talk about we will discuss the sequence impedances of the different power system components, and we have now covered the Y connected loads. So we in this lecture have determined now the sequence impedances of Y connected load, and we started the discussion with the case where the Y connected loads where the neutral point was connected to the ground. So we found for this particular case where the neutral was connected to the ground through Zn impedance, so we found the three sequence networks, and we found that these three sequence networks are uncoupled. These are not coupled networks, and we made some observations. The important observation was that the zero sequence network in the zero sequence network where the zero sequence current is there, so through the impedance to the ground only zero sequence network flows. The other two currents, other two sequence current, positive and negative sequence currents, they do not flow through the impedance to the ground. It is only the zero sequence current which flows through the impedance to the ground. And we also then discussed that, let's say if the neutral point is not connected to the ground, then the zero sequence network will be open, which is shown here. And then we also solved an example. So we have now, with this discussion, we have now covered the sequence, the discussion related to the Y connected loads, or the discussion related to the sequence impedance of the Y connected loads. So I will discuss the other components of the power system, or the sequence impedances of the other components of the power system, in the next couple of lectures. So with this, now I end this lecture, and once again, if you have any query, you can note it down, and we will discuss that in the interactive session. So thank you very much for your attention, and with this I would end this lecture. Assalamu alaikum wa rahmatullahi wa barakatuh.